We're continuing our deductive reasoning arguments today by proving some statements about segments and angles. So we'll just be trying to fill in these blanks. 3 steps of a proof are shown. They call it a proof because deductive reasoning, there can't be a counter example that shows up. We've actually proven it's true, it's not just a conjecture. We're going to give the reasons for the last 2 steps. The given is that the length of BC is equal to the length of AB, and you can see that they put the tick tick on the picture already. And we're supposed to prove that the length of AC equals the length of AB plus the length of AB again. And so let's see how we can do. You'll see first that they put the given information right away at the top. It's our job to figure out how they knew this was a true statement. How do we know that the length from A to C is equal to the length from A to B plus B to C? And that's something we learned last chapter. How do we know that those 2 shorter lengths add up to make the longer length? That was called the segment addition postulate. This next statement, again, we have to figure out what reasoning did they have to say that that was true. And one thing you should watch for on these is sometimes the line before is related to the next line. Can you see the similarities? We've got AC here, we've got AB here, and the only thing that has changed is that BC has been replaced with AB. Why is it a legal move to replace a BC with an AB? The answer is because they're equal to each other. So that's okay to, what's the word? Substitute, to replace AB for BC. Can I just tell you right now that nobody feels very good at these when they're first starting out, but the more examples you see and the more of them that you try, I promise you'll get better at this. Just don't give up. Here we are given that point R is the midpoint of segment AM, and also that the length MB is equal to the length AR, and we're trying to conclude that M is the midpoint of RB. The first thing I might do is just put some markings on the diagram from those given that says that R is the midpoint of AM and MB is equal to AR. MB is equal to AR. So that was a given. And I know that R is a midpoint. So those were my givens. Now let's think about what it means to be a midpoint. What does it mean for R to be the midpoint of segment AM? And hopefully you remember, I can't resist. Whenever I see a midpoint, I just have to go tick, tick. I know that if R is right in the middle, that those 2 parts are congruent. So that's the statement that goes next to definition of a midpoint. Segment AR is congruent to segment RM. Here's a funny little reason. It says definition of congruent segments. What does it mean to say that 2 segments are congruent to each other? It means same shape, same size, so we can say that AR, the length, is equal to RM, the length. And you'll see that a lot. The definition of congruent segments is just used to go from congruent to equal. Or it could go the other way because definitions are biconditional. We could go from the equal to the congruent. So why would we want to do that? Why would we need an equal sign? Sometimes when we're doing those algebra problems, an equal sign will work better for us. Here we've got segment MB. The length is equal to RM's length. How do we know that? Does it come from the picture? Does it come from the statements up above? I think we can kind of see that aren't all 3 of those ticked now? All 3 of those are congruent to each other. So we must have had some overlap there, right? We had MB equal to AR, and we had AR equal to RM. I'm wondering, do you see a train there? Since MB was equal to AR and AR was equal to RM, we can say that MB is equal to RM by the transitive property of equality. For the next line, our clue is that the reason is definition of congruent segments. Remember, we just did that in this third step up here, and I told you that definition of congruent segments is used to switch between congruent and equal signs. So that's your clue. Switching from congruent to equal signs or back again is what we'd be looking for. So if you look at that previous statement, it was an equal sign, right? So what we're going to do is switch it to the segments are congruent to one another. So things got switched to equal signs, and then they got switched back to congruent signs. But there was a good reason for that, because the thing that we were trying to conclude, the thing that we were trying to prove, is that M is the midpoint of segment RB because those two pieces are congruent. And so that's why we just made that statement that MB was congruent to RM, because now we can say that M is the midpoint. How do we know? Because that's what a midpoint does. It cuts a segment into two congruent pieces. So this would actually be definition of a midpoint again. If you looked up midpoint in the dictionary, it would tell you that it's a point that cuts a segment into two congruent pieces. And remember that definitions are always biconditional, so if we had two congruent pieces, then we can say we've got a midpoint. And both of those reasons would fall under definition of a midpoint. Again, I know this might feel overwhelming, but we're just going to keep going. We won't give up. Use the diagram to prove that the measure of angle 1 is equal to the measure of angle 4. And I sort of believe that because aren't those vertical angles? And we've always talked about how vertical angles are congruent to one another, but we don't really have a reason to back it up yet. So we're going to go through this logical argument to show that it must be true. So in this diagram, it's given that angle 2 and angle 3 are equal. Swoop, swoop. Already marked there. Also, the measure of angle AXD, that's the big combo of angle 1 and angle 2, is equal to the measure of angle AXC. AXC would be this combo of angles 3 and 4, right? So those are our givens. And I was just talking about a combo of two angles. What was angle AXD made up of? AXD was that top one made up of angle 1 and angle 2. That's the angle addition postulate. The angle addition postulate tells us that two smaller angles add up to make that bigger angle. AXC, if you look at the picture, is a combo of angle 3 and angle 4. Now we have to figure out where this statement came from. A 1 plus a 2 equals a 3 plus a 4. I don't see anything on the picture that tells me that, so it must have come from these up above statements. Always check above to see if they're using that stuff to make the next statement. Do you see where it says angle AXD was equal to angle AXC? Well, here's the thing. AXD is equal to 1 plus 2. So maybe that's where that part came from. The 1 plus 2 came from the AXD. And AXC was equal to 3 plus 4. So that's where this 3 plus 4 came from, was the AXD. So what happened going from step 1 to step 4? We just did a nice big replacement. We replaced AXD with 1 plus 2 and AXC with 3 plus 4. What's the property that lets us replace things? The substitution property. Now step 5 says angle 2 is equal to angle 3, and I don't really see anything up above that tells me that. And that's when I realize, oh, that was one of my original given statements. Why did they save it until now? Well, sometimes you don't bring up those givens until you're ready to use them. So do you see going from step 4 to step 6? There's a lot of similarities here, right? Angle 1 plus was angle 2 equals angle 3 plus angle 4. So I am guessing that they must be doing a substitution right here. Are you seeing it? And what can we substitute? There it is. What can we substitute for an angle 2? Angle 2s are equal to angle 3s, so I can put an angle 3 right there. Now the final step brings us from that equation to this equation. What is different between equation 6 and equation 7? Hopefully you notice that there's no angle 3s in that final step. Where did the angle 3 go? Since it's an equation, I bet it just got subtracted off of both sides, do you suppose? So to get from 6 to 7, you can use the subtraction property. All right, just one more, and I promise the more you do, the more this will start making sense. If you know that ray BD bisects angle ABC, prove that the measure of angle ABC is 2 times the measure of angle 1. And we've got a diagram over there, and the given is the if part, so we've got BD bisects ABC. That first part is given. And we're supposed to prove that the measure of angle, did you know that the thing we're trying to prove will always be our final statement? Because once we make that final statement, that would mean that we're done with the argument. So that's something interesting. Usually the givens appear at the top, sometimes partway through, but the final thing we're trying to prove is always the last statement. We don't know yet what to put here. We can't just put prove, but it'll have some logical reason as we come down this chain. One thing you're going to start to notice is whenever you see words in the given, we're almost always going to use the definition of that word as one of our reasons. Because BD is bisecting angle ABC, that has a very special meaning. And so if you looked up angle bisector in the dictionary, it would say that it's a ray that splits the angle into 2 congruent pieces. And so that's what we're going to say. The definition of angle bisector tells us that angle 1 is congruent to angle 2. So sort of like definition of a midpoint. If you see that word bisector, then you can write that the angles are congruent. This also looks a little familiar. We talked about definition of congruent segments on a previous one. Definition of congruent segments just allowed us to switch from congruent to equal measures, or from equal measures back to congruent, and that'll work for angles too. So we had those congruent angles 1 and 2. Now we would want to switch that to an equal sign, and when we switch to an equal sign, we put the little m on front. The measure of angle 1 is equal to the measure of angle 2. And it makes sense that we would want to switch that over to an equal sign because the final conclusion we're trying to make has an equal sign in it. Step 4, can you see any good reason why the measure of angle 1 plus the measure of angle 2 would equal the measure of angle ABC? The clue is in the picture. The measure of angle 1 plus the measure of angle 2 makes the measure of angle ABC, because 2 smaller angles added together makes that larger angle. That's a postulate. What was it called? The angle addition postulate. Next, we've got the substitution property, which usually means we're taking an equation from a previous step and just changing a little bit. So angle 1 stayed the same, angle ABC stayed the same, but we're going to do our substitution or replacement right here. what could I replace for the measure of angle 2? And I would say, since the measure of angle 2 equals the measure of angle 1, I can put an angle 1 right there. And you know what? I just changed my mind. I feel like I might need one more line for this. Let me show you why. Can you help me simplify a measure of angle 1 plus a measure of angle 1? What do you get? You get 2 angle 1s, 2 measures of angle 1. What do you suppose we would use for the reason that we can combine measure of angle 1 plus measure of angle 1 equals 2 measures of angle 1? I'd probably just say simplify or combine like terms. The reason I decided to add one more step is because, we get to use one of our new properties. Here I've got 2 measures of angle 1 equals an ABC. Here I've got an ABC equals 2 measures of angle 1. Do you see how they just switch sides? What do we call that property? Switch sides symmetric property.